Hello, BMB 510 MNE 525 class. This is the second part of the week, Operation Parameters and Bioreactors. So a little bit more on operation of bioreactors before you dig into the assignment that's been posted on my courses. So overall, there are two main types of bioreactors. There are stirred tanks, and that includes things like CSTRs and even stirred batch reactors. There are bubble columns, which, as you'll see later, can take different forms like airlift reactors and straight bubble columns, as well as packed bed and other types. The key difference between these two things is how agitation is performed, and agitation begets mixing, as you can imagine. So in stirred tanks, we have an impeller attached to a shaft, and some shaft work is done to assure good agitation and good mixing. Whereas in bubble columns, it is simply the force of gas or air being sparged through the liquid that is going to give us the agitation and the mixing that we hopefully will need. Okay, so first with stirred tanks. You can see here a schematic of a stirred tank with turbine impellers and other goodies, inlets and outlets and such. And these are widely used bioreactors, especially as fermenters. In fact, I have a stirred tank bioreactor in my lab. They're vertical cylindrical vessels, and they're equipped with a mechanical stir, hence the name stirred tanks. So in order for mixing to occur, shaft work must be done. And the stirrers rotate around the axis of the tank here, and you can see the position of the stirrers in this schematic of a stirred tank. So what is the objective? The objectives of a stirred tank in terms of liquid mixing is to make the liquid concentration, which will contain some cells, it'll contain growth media, it'll contain other stuff. It's going to eventually contain product. It's going to contain waste products. Make the liquid concentration in there as uniform as possible, including dissolved gas like oxygen. We want to suspend particles or cells in the liquid. We would like to potentially disperse liquid droplets in other immiscible liquids. For example, we could be running a fermentation using oil as a carbon source, so dispersing oil and water in that way. Stirred tank mixing could help us do that. And we want to disperse gas as bubbles in liquid, as well as potentially transfer heat from or to a liquid. And oftentimes with the heat generated by metabolic activity, we're transferring heat from the liquid to the outside, so as to not overheat the culture itself. Alright, so to do mixing, we need mixers, otherwise known as impellers. And some of them, you may see cartoons of them. They look kind of like propellers on a plane or a boat. Very few are actually like that. We'll see later what they generally look like, what the most common accepted variety of impellers look like. But their job is to create local turbulence near the blades, which allows mixing to occur. And mixers will circulate all the liquid through this region, so there are no unmixed pools in any part of the reactor. So we don't want any dead space in there where things are going to go unmixed. We also want to avoid local gelation, which could happen especially if we're dealing with filamentous yeast or some other viscous liquid of some kind, or formation of clumps of cells, because these will tend to resist separation and mixing. So we don't want that. And like I said, there are types of impellers, and the one maybe you might think is most common here is this propeller. Propellers are used. They're good because they cause less cell damage, so they can be potentially good for things like animal cells. But they are rarely used in bacteria and yeast fermentations. If we're dealing with bacteria and yeast, we will use something like this. This looks like a flat disc. It's called a 6-flat blade disc turbine. You can see it's got blades sticking out of it. It's also known as a Rushton impeller, and I will refer to it as a Rushton impeller going forward here. And there are things like anchors, gate anchors, these two guys here, which are designed for higher viscosity products. The paddle is used over a wide range of viscosities. And things like the helical screw that are less common, which are very highly viscous fluids and you're operating at a low RPM. Okay, so I said about the 6-blade flat disc impeller here, the Rushton turbine is what it's called. And there are some standard dimensions for this impeller relative to the tank size. And you can see some schematics here. But if we're looking at what is called D over D, or the impeller diameter over the tank diameter, is typically 1 over 3, 1/3. The diameter of the tank is often equal to the total liquid depth of the HL here, so the D equals HL in most cases. L over D, L is the length of the impeller blade, divided by the impeller diameter. That should be about 1/4. You can see L is denoted here. It should be about 1/4 of the diameter of the entire impeller. And B over D. B is the width of the impeller blade. You can see B right here. And B over D is 1/5. And so these are some standard dimension of the Rushton turbine impellers. And so the purpose of these impellers is to move liquid in a tank. And when a Rushton impeller is used, and they're typically in most fermenters, just same as in the one that's in my lab, it has typically 4 vertical baffle plates. You can see the baffles indicated here on the sides of the tank. And again, this allows for more mixing. Each baffle plate is 1/10 of the tank diameter in width. The shape and size of the impeller prevents circular flow of fluid. So it prevents a little vortex or a little whirlpool from forming in the center of the tank where the mixing is happening. And that prevents the formation of such a vortex, which leads to bad mixing and it leads to bad oxygen dispersion, etc. So you can see you have some regular mixing patterns that can develop when the the turbine is moving, when the impeller blades are moving in a baffled tank, where you get some mixing down below the impeller and you get some mixing above in separate packets, which is good for dispersion of everything in the fluid. Liquid is sucked into the impeller center from below and above, and you can kind of see that here with the direction of the arrows, where the liquid getting sucked in here and then flung to the sides. It's driven radially towards the tank wall. Again, as you can see here in these with these arrows in this drawing. At the tank wall, liquid is then deflected upwards and downwards, which again you can see right here. And impellers like our Rushton impeller are known as radial flow impellers. And you can perhaps see why, considering how they do their business. And when liquid mixing is accompanied by aeration, which is often is, the gas is dispersed due to the high shear rates that are produced by this impeller here. And incidentally, this is why impellers like this aren't good for mammalian cells necessarily, because they can produce these high shear rates which will destroy cells that do not have cell walls. So we've talked about the shaft work, we've talked about the stirring, we've talked about the mixing. That means power requirements. So what are the power requirements of stirred tanks? Essentially, the power required to operate a stirred tank fermenter is found mostly in the mechanical power required to rotate that stirrer. The power requirement will increase the bigger the tank and the more the rotating speed. Power will also vary according to the properties of liquid. So if we're using a more viscous liquid, we're going to need more power to rotate that stirrer. Stirrer power requirements for gas liquids are generally less than for ungassed liquids. And this is due to the average bulk densities of the fluid. So fluid with gas dissolved in it has a different bulk density than that which has no or not much gas dissolved in it. And you can think of this in terms of power ratio. And in your homework you will be asked to calculate a power ratio. This is the ratio of power requirement for a gas-sparged liquid in a stirred tank, PG, compared to that of an ungassed liquid, PO. And it is this complicated equation here, where we have D, our tank diameter, little d is our impeller diameter, just to be confusing, N is the rotational speed of our impeller, why N I don't know, Q is our gas sparging rate or our gas flow rate, nu here, this Greek letter nu is the kinematic viscosity, and of course G is that gravitational constant you all remember from physics. This equation is based on stirred tank data that was taken using 6-blade flat turbines. And so typically this will fit in tanks that have these types of turbines in them. And the equation applies to stirred tanks where liquid to depth diameter ratio, or liquid depth to diameter ratio, is typically around 1. And you find that typically that is what is going on. Your D, your big D here, is going to be equal to your HL, or your liquid depth. And what this equation actually is a bunch of dimensionless numbers. It's a dimensionless thing because PG to PO is a ratio. But these are a bunch of dimensionless numbers together here. And again, you see what they are here. You know, here's our ratio. It's a dimensionless group. But the equation is made up of the Reynolds number, which is this term right here. We have the Froude number, or FR, which is this number right here. And we have the aeration number, or NA, which is right here. And this is a diameter to diameter ratio. So it is also dimensionless. Now we want, what do we want? We want KLA. Doesn't matter what tank it's in. KLA is important, especially if we're talking about distributing oxygen in the tank here. And when dealing with KLA and gas-sparged stirred tanks, it's actually more rational to separate the two. You know, to take them at their individual KL and A, as both end up being affected by different factors. A can be measured by light scattering or by the chemical method, and we talked about that on Tuesday, whereas KL we can find a different way. The average bubble size, or the DVS here, can be estimated below, where we using this equation here. And here's our A from the KLA, and we have the epsilon, which is the gas holdup, if you remember, and here's our average bubble size. So what if we really want KLA, and we're not just doing this in a tank full of water? Well, it's more practical if KLA in gas-sparged stirred tanks were to be directly correlated with actual operating variables and liquid properties, as opposed to just running water in a stirred tank all the time. So the below equations can be used to produce a very rough estimate of KLA in sparged stirred tanks. And there are two equations here. One is for volumes of less than 2.6 meters cubed, and the gas sparge power requirement, the PGV ratio, is between 510,000 watts per meter cubed. We would use this equation. And for air electrolyte solutions, and again the V is less than 4.4 meters cubed this time, we have a PGV again of between 500 and 10,000 watts per meter cubed. We would use this right here. And generally, when we were talking air electrolyte solutions, if we're pumping air into a tank that is full of growth media, that would constitute an air electrolyte solution. make no mistake. And you see this UG term in both of these equations. That UG is the superficial gas velocity. Alright, in stirred tanks it can be assumed that the liquid concentration is uniform. We're assuming the stirring has made everything uniform. This is true for small vessels, lab scale vessels, where the rate of gas-liquid mass transfer at the free liquid surface is a large proportion of the total mass transfer. Again, because of those small volumes. So liquid mixing, to be really general about it, refers to the macroscopic movement of liquid, what we would call macro mixing, which is what's going on here in this drawing right here. More micro mixing, well, that's diffusion, although that does play a role, of course. But generally, we think of the impellers as promoting macro mixing. Mixing time, if we're thinking about mixing time is a practical index of the degree of liquid mixing. So the shorter the mixing time, the more intense the mixing. And we can determine mixing time. Again, if we have a stirred tank full of water, we inject a little dye into the stirred tank at one area, and then we see how long it takes before the pulse of color comes back to the same place. And as you mix, it's going to take less and less time for the pulse of color to come back, because basically we're mixing. So how long it takes before this pulse of color, this pulse of dye, comes back to the same place, that is known as TC. And mixing time in general, TM, is equal to about 4 TC usually. And you can see here the TCs are spaced out, between every apex here. Okay, so let's do an example here of mixing time. So we have a stirred tank reactor equipped with a standard Rushton turbine, which contains a liquid with density 1 gram per centimeter cubed, viscosity of 0.013 grams per centimeter second. The tank and the liquid depth are both 2.4 meters. So it's that 1-to-1 ratio, and the liquid volume is 10.85 meter cubed. Our impeller diameter is 0.8 meters, and let's estimate the mixing time, our TM, when the rotational stirrer speed, or our N, is about 1.5 per second. So first we can determine the Reynolds number, and in a stirred tank, you determine the Reynolds number using this equation right here, where N is our stirrer speed, D is our impeller diameter, and rho, of course, is our density, mu is our viscosity. And so we can easily plug all these things in because we have all those values, and we get 7.38 times 10 to the 5th. That's our Reynolds number. So that's highly turbulent, as you can imagine, and that's the point. For good mixing, you want turbulence, and that's what you get in a stirred tank. Now we want to estimate or find or estimate the power number. And how do we do that? Well, we have the Reynolds number right here. We can use this chart below to estimate the power number, our NP, which is equal to this. P divided by N cubed, D cubed, N cubed D to the 5th times density. And so we look, here's our Rushton turbine, so we want this trace right here. And so we have our Reynolds number. Let's estimate it to be about here. And we bring it over. It's tough because there's a big gap here. But let's say it's about 6. The NP, our power number, is about 6. Let's call it that. So now we have the NP, we can estimate the power required for mixing, which is, again, you see here as P power required divided by n cubed d to the fifth, and rho, or density, that is the power numbers. We just rearrange that equation here to solve for P. And we get 6,650 kilogram per meter squared second cubed, i.e. 6650 watts, or 6.65 kilowatts. So it's 6.65 kilowatts, which is the power required for mixing. Finally, we can determine mixing time. So this chart, again, we use our Reynolds number. We can estimate the mixing time times the stirrer speed, our Tm times N. We have a Reynolds number, 7.38 times 10 to the fifth. Wait a minute. Okay, this doesn't go far enough. And believe it or not, where I got this from doesn't go that far. The same chart doesn't go that far either. But you will notice that it kind of levels off here. So we can estimate that we just extrapolate here. The N times Tm is probably going to be around 30. We estimate that it's going to be around 30. Again, this is an estimate. And so if we do estimate that, we estimate that N times Tm is 30, we can then solve for Tm by dividing by N, and we get 20 seconds. So our mixing time is 20 seconds in this case. Alright, so we've talked about stirred tank reactors. Let's move on to the interesting bubble column reactors or fermenters. So there's no mechanical agitation with these guys. The agitation is done, the aeration and the mixing is achieved by the gas bubbles floating up through the liquid here, by gas sparging. And sparging is typically done in bubble columns from bottom to top. Sparging is typically done in most fermenters from bottom to top. Power requirement, well, it's power requirement for gas feed only. So it's a lot less than stirred tanks of comparable capacities, which could be a good thing if you're trying to save money in your electric bill. There are no moving parts. Again, you're just blowing air through here. It's an easier scale-up. Bubble columns are an easier scale-up. And there are two types of flow regimes you can do for bubble columns. There's what's called the homogeneous flow, which is at gas velocities that are low, between 3 and 5 centimeters a second. And you can see kind of a schematic of homogeneous flow right here. It's known as quiet flow. Bubbles are evenly distributed along the diameter of the column. And so you can see that the bubbles are evenly distributed here. But oftentimes we want to be at heterogeneous flow, which is at higher gas flow rates. And that's known as turbulent flow. And you can see there we get some flow patterns here. Like here, we have heterogeneous flow. We're seeing some circular flow patterns in the fermenter, in the bubble column fermenter. And that is going to promote mixing. So if we want to really promote mixing, we would rather be at heterogeneous flow, at those high gas flow rates. Okay, and so kind of the general flow of liquid, you can imagine the spargers down here at the bottom somewhere. The liquid gas mixture, the gas and the liquid, they're going to be propelled upwards in the central region. And you can sort of see that by the way these bubbles or these flow patterns are moving. And they'll move downward in the annular region, near the column wall. And again, you can see that by the way these flow patterns are shaped here. The flow pattern is caused by differences in bulk densities of the liquid and gas mixture here. Usually a uniform liquid composition can be assumed when we evaluate our KLA, which we'll talk more about KLA in a bit, except when the height diameter ratio is very large. And that doesn't happen too often with bubble columns, but sometimes it's necessary when you have a really tall, thinner version of the bubble column. Okay, so we can estimate gas holdup here. Like we talked about gas holdup in the stirred tanks. Gas holdup in bubble columns can be predicted using this equation below here. Again, fraught with dimensionless numbers. So here's gas holdup and 1 minus gas holdup to the 4th here. And so here is 0.20 times this term here, which is known as the bond number. And then that's to the 1/8 power. This term here, which is known as the Galilei number, probably named after Galileo Galilei. Not that that matters. But this is the Galilei number to the 1/12th, multiplied again by our Froude number here, right here at the end. And you can see there is a surface tension term here in the bond number. So you need the surface tension to figure out the gas holdup, or to estimate the gas holdup in a bubble column. Similarly, we can figure out KLA using a bunch of dimensionless numbers. Again, so DL is our liquid phase diffusivity. And the equation here was based on data from 4 different columns, each having a diameter of up to 60 centimeters. Again, with the dimensionless numbers, the kinematic viscosity over the liquid phase diffusivity, that's known as the Schmidt number. Again, we have the bond number here. And again, we have the Galilei number here. And then at the end here, we have our gas holdup, which we found from this equation. Bubble size. This is another one. Bubble size has been studied in column reactors like this. And that's by the photographic method. Again, kind of the crude method where we take pictures of bubbles and sort of measure their size using some sort of software. The largest fraction of bubbles in reactor study was greater than or equal to 1 millimeter. So most of them are going to be greater than or equal to 1 millimeter. The average bubble size is affected by the Sparger design, or the Sparger size. So keep that in mind. But bubble size can also be affected by coalescence and breakup rates. And we'll talk a little bit more about what that means. So again, we see we have dVs over the tank diameter is equal to 26 times the bond number again to the negative 0.5 power, the Galilei number again to the negative 0.12, and the Froude number again to the negative 0.12. And dVs is the volume surface mean bubble diameter. So I mentioned coalescence of bubbles. What does that mean? Well, coalescence of small bubbles into larger ones. And that's usually undesirable. And you can see an illustration of this right at the bottom here. These are 2 bubbles coalescing into one bigger one. You don't want that usually. Frequency of bubble coalescence will depend on liquid properties, though. Pure water is known for being a coalescing liquid, so it allows or fosters coalescence quite readily. In non-coalescing liquids, however, bubbles tend to bounce off each other. They don't coalesce as readily. And the presence of salts in aqueous solution will suppress coalescence. And guess what? Cell growth media will contain all kinds of salts. So it's less of a coalescing liquid than you might have thought. And we can figure out the interfacial area here. And so we have, again, our interfacial area times d, the tank diameter, is equal to 1/3 times the bond number to the 0.5, times the Galilei number to the 0.1, times the holding, the gas holding, which is the gas holdup, which is gas holdup to the 1.13. To get KL alone, we can use our Sherwood number, which is equal to KL times the average bubble diameter divided by the DL, the liquid phase diffusivity. Or we can multiply 1/2 times the Schmidt number to the 1/2 times the bond number to the 3/8 times the Galilei number to the 1/4. So we can get our KL in a number of ways. There are special types of columns called airlift reactors. These are bubble columns, but they do different things. So we have basically we have a physical separation of the upflowing and the downflowing. And you can see in these schematics here that the upflowing gas is separated from the downflow. And there are two main types. There are internal loop or IL vessels, and this is where we have an internal loop right here, where we're either going up the middle and then down the sides, or up the sides and down the middle. And then there is external loop vessels, which is up one side and down the other. So you have basically a riser and a downcomer separated, as opposed to having in one tank a riser and then a downcomer. So here the riser is right over here, and the downcomer is over here. And mixing is usually better in internal loop vessels. There are special kinds of airlift reactors called deep shaft reactors. And these are tall internal loop airlift reactors built underground. These are deep shaft reactors, and they have very high hydrostatic pressure at the bottom of these vessels here. And this one looks like it goes down about 300 feet. And this considerably improves gas-liquid mass transfer. And oftentimes you can see a schematic here. You see things like names like sludge, influent, all that stuff. They're often used in waste treatment, these deep shaft reactors. There are special types of reactors that are called packed bed reactors. They're kind of like bubble columns, except we have a packed bed with catalyst particles here. And of course we talked at length about catalyst particles last time. These are used with immobilized biocatalysts. There's several applications that can be used. Namely, we've got an amino acid and a central metabolite that can be produced in this way. We can resolve amino acid isomers in this way, and a variety of other things. And the mass transfer is facilitated at high liquid flow rates. Aeration is often done separately, and the water or the liquid is just pumped through by a pump, as opposed to being aerated in the actual column itself. This is unsuitable for applications that result in trapped gases such as CO2. So if there's a lot of CO2 being used or evolved, you don't want to use a packed bed reactor. An idealized simple case of a reaction with Michaelis-Menten kinetics, we consider mass transfer effects to be negligible. Maybe that's a stretch considering what we talked about on Tuesday. But we have a reaction rate equation where U is our fluid velocity through the bed is equal to this Michaelis-Menten U times the change in the substrate concentration over the change in height of the bed is equal to this Michaelis-Menten looking equation right here, this negative Vmax times Ca divided by Km plus Ca. The required height of the bed looks a little like this, where Z is equal to U times Km Vmax times the log of the initial concentration of substrate divided by the final concentration of substrate, and that's initial concentration of substrate going into the column, and the final is concentration of substrate going out of the column. And again, plus CAI minus CAF divided by Vmax. The reaction time in this would be the height, the Z, divided by that fluid velocity. Okay, and lastly, we talked about, or I mentioned that I would talk about microreactors very briefly. These are miniaturized systems, and these have fluid channels and reservoirs of very small dimensions. The channels can be anywhere from 1 millimeter down to as low as 0.05 millimeters in diameter. Currently, microreactors are generally used for analytical systems, so to maybe adjust reaction and fermentation conditions on a small scale and on a micro scale, and you can potentially do many of these at once, depending on the setup you have. It is feasible that microreactors could be used for small-scale production because of the larger specific interfacial areas. We have small fluid layer thicknesses that allow that. small fluid channels, small Reynolds number. Often we're operating basically in laminar flow, not really turbulent flow. They're more compact, and there's no scaling up problems. And there is a company in Woburn, Mass. Called Farrex Incorporated. They produce these little microbioreactors here, and you can see the little channels here, and they have little entry ports up here at the top, and you can see the channels. They go off to different reservoirs, and these reservoirs are put on kind of a platform that will pump them a little bit and allow for some mixing and allow for movement of the fluid. And you can see there are these sensors here in the different cavities, and they can tell things like dissolved oxygen concentration, pH, etc. And you've got reservoirs for things like acid and base to control the fermentation. So you can visit them and look at their website, see some pretty pictures of what they do. That's at www.farrex.com. And those are microbioreactors, and they're more and more commonly used these days. And again, currently they're used in analytical purposes, but they're really neat. And the kind of the physics behind them and the biochemistry behind them and the mechanical engineering behind them, it's all very neat. So take a look if you're interested. Okay, so that is it. There is a homework posted on my courses. That will be due not next Thursday, but the Tuesday afterwards. I'm not in much next week. We will not have class next Tuesday, but we will have a flipped class on Thursday. So please come to class next Thursday. You'll have an assignment on Tuesday, and you'll have an in-class thing to do on Thursday. So please make sure you get those done. Those will be posted along with a video lecture, hopefully by before Tuesday, so hopefully by Monday, so you can get those done in time for class on Thursday. And I will see you then.